Okay, can you hear me?
We get it, yeah.
Okay, so thank you. I'm Markus Luty. I'm going to be talking about four-dimensional renormalization group flows and conformal field theory. I'm sorry for the mystery. The organizers never asked me for a title. This is what I planned all along, so I'm sorry if it's a surprise. This is going to be a more theoretical topic, so I guess maybe the thinking of the organizers was after 3 weeks you can use some entertainment. But I have bad news for you. I didn't prepare any jokes, but that's okay because usually when I give lectures, people end up laughing even though I don't make jokes. So, for example. Okay, so just to motivate the subject, okay, I don't think I need to motivate the study of four-dimensional RG flows, so I'm going to motivate conformal field theory. And of course, I will define exactly what conformal field theory is, but you probably have heard the name, which would be enough for the motivation. The first point is that if we look at RG flows of arbitrary quantum field theories, we find that in all known non-trivial cases, the infrared asymptotics of the RG flow is a conformal field theory. And furthermore, whenever the conformal field theory is UV complete, the UV asymptotics is a conformal field theory. So it appears, as far as we know, that all non-trivial RG flows within quantum field theory start and end at conformal field theories. Okay, so understanding conformal field theories is understanding the endpoints which, in a sense, define the quantum field theory. Okay? And by the way, when I say quantum field theory, I mean in any number of dimensions a theory that is Lorentz invariant, unitary, etc. That's what I mean by quantum field theory. A second motivation, so one motivation for CFT is RG flows asymptote to a CFT, both in the UV and in the IR. The second motivation is the ADS-CFT correspondence. So ADS in d+1 dimensions corresponds to a conformal field theory in d dimensions. And this correspondence goes both ways. If you're a CFT guy like me, the interesting direction is actually this way, because this theory over here is quantum gravity. Okay? And quantum gravity is truly different. Quantum gravity is not quantum field theory. Unfortunately, I don't think I'm going to be able to have time to talk about this at all, but this is a really important point. Okay? And so the fact, however, that certain theories of quantum gravity are explicitly described by an ordinary unitary d-dimensional conformal field theory is extremely important because it allows us to address the mysteries of quantum gravity in a much, much more controlled way. The third motivation for studying conformal field theories is that these are examples of quantum field theories with extra symmetry. Okay? And in fact, it's an extra space-time symmetry. Okay? So conformal symmetry includes symmetry under scaling, under scale transformations, which are obviously space-time symmetries. And so this extra symmetry actually leads to new structure. So it's not just that you have, fewer reduced matrix elements and you have a bigger set of Clebsch-Gordon coefficients. It's much more than that. You have entirely new structures that appear in conformal field theories that don't appear in ordinary quantum field theories. And a very close analogy here is supersymmetry. Supersymmetry is an additional space-time symmetry which also gives us a rich new set of structures, and we can learn a lot about quantum field theory by studying the special, more symmetric case. Okay? And then the final motivation, because we're here at phenotasy, is phenomenology. Okay? So phenomenology is also a motivation for studying this. There are many possible ways that the conformal field theories could play a role in phenomenology, and all you have to do to see that is to look at the 10 to the third papers on the Randall-Sundrum model, because the Randall-Sundrum model is a conformal field theory. So I just want to make one comment, and then I'm going to leave phenomenology for the rest of my lectures, and that is that the RS model is, again, via this ADS-CFT correspondence, dual to a large n CFT. Okay, so if you don't know what n is in Randall-Sundrum, it's basically in the Randall-Sundrum language, it's the weak coupling parameter that gives you theoretical control. So large n gives you theoretical control. That's why there are 10 to the third papers written on this. However, this is also bad for phenomenology. In almost every case, what you really want is a CFT with n of order 1. But the problem is it's not calculable. Okay, so these are exactly conformal field theories. That's exactly the subject of these lectures. So that's what I have to say about motivation. Okay? So I do hope people will interrupt me, because I get very nervous when people don't interrupt me, and you don't want to have me lecture to you when I'm nervous. Okay? So please interrupt me. Okay? Any interruptions so far? I'm getting nervous. Okay. All right. Yes. Right, I'm going to talk about that. So let me defer that question, because I'm going to talk about exactly that point. Okay? Okay, so what I want to try to give you a bit of an outline or a teaser or something, I'm going to say that it's not just that it's an interesting subject, but there's actually been real progress that's been made in the last few years. Okay, so first of all, let me stay over here. Okay, so first of all, I'm going to be talking about 4G RG flows. Okay, and one of the results that's been obtained is that that CFT, that any QFT indeed goes to a CFT with one major, very important asterisk, okay, that's provided both in the IR or the UV. This provided that the infrared asymptotics is described in perturbation theory. Okay, so these are things I'm going to explain in these lectures. There's also non-perturbative proof of RG irreversibility. Okay. Namely, if we have a UV complete quantum field theory that starts off as a UV CFT and flows in the infrared to some IR CFT, okay, if this flow is possible, then the reverse flow is not possible. And in fact, there is a theorem that there's a quantity A, which you can calculate here and you can calculate here, and AUV is always bigger than AIR. This is the so-called A theorem, which is a general result in four-dimensional quantum field theory that is independent of perturbation theory. So I'm going to describe that.
What is the statement that the reverse flow is not possible?
Oh, because of this, right?
No, I'm just asking what a reverse flow is not possible.
Oh, it means that okay, well, so what this kind of a flow, the way it happens is that, well, I'll tell you what, let me defer that question as well, okay, because we're going to get much more into this, okay, because I'm going to be talking, because if I start explaining that, I'm going to start, okay, so hold on to that question, okay.
Is this related to the fact that if you start from UV theory, you have a unique IR effective field theory, but that's 5%. If starting from the IR effective field theory, you don't know what exactly the unique theory composition.
That's right. That's part of the intuition of this. But this is a very, very precise result, right? Because the thing is that here I'm looking at one particular UV completion, right? And you may still imagine that just like this UV completion could also, in principle, flow to other places, okay? So it's not really just a question of uniqueness, okay? And many other guys could flow into this guy. That could also be the case. But it's the statement that these particular asymptotics cannot be reversed. There's no other path around like this, no matter, even though this diagram can be very, very non-trivially connected. Another way to think about it is that if I view this as the space of all quantum field theories, there's a height function on it, which is A, okay? And you always go down. That's not an obvious statement at all. Right? How do I know that some clever model builder could not find some way of going from here back to here? Okay? If you like, the intuition that's usually invoked is that we're integrating out degrees of freedom when we go into the infrared. Okay? But that intuition is also, there are counterexamples to that intuition. Okay? The intuition, not this result. Okay? Okay, so let's hold off on that. Okay, we can talk about this more. Right now what I want to do is I want to get through a laundry list of the things that I'm going to try to describe in these lectures. Okay, and then I'm going to describe them, and that will be the time to ask the questions, if you don't mind. Okay? What's that? I'm going to tell you what this A is later, but not now. I will tell you, though. Okay? I'll tell you more precisely than you probably want to know. Okay. And the last item that goes under sort of 4D RG flows, and I'm not going to write this out, but there's a non-perturbative argument that scale invariance implies this larger group of conformal invariants, which again, I'm going to tell you later exactly what that means. But this argument, I claim, is not complete. It is, however, highly suggestive. So even though it doesn't quite work, I think it's interesting enough that I'm going to talk about it. No. I thought I did. No, I never thought I did. Other people thought they did. Think they did. They still think they did. But I'm going to tell you that they didn't. Okay? So this topic may be a bit controversial, but I'm going to give you my take on it. Okay? And then, so by the way, I should say, sorry. I should point out that, sorry, we already did a question. In perturbation theory, it's absolutely true by this result, right? In fact, this is a much stronger result. It says the only thing that's possible in the infrared or the UV is conformal field theory. The only question is, could there be some weird non-perturbative exceptions? And this is the argument that tries to rule that out. That's what's controversial. Okay, the perturbative case is not controversial at all. Okay? All right. Okay, so that's the set of things I want to try to tell you about 4D RG flows. The next set of things I want to tell you is about conformal field theory. But you know what? I think I'm going to defer the list of things that I'm going to tell you until I actually tell them to you. Okay? So I'm going to skip that for now, and I'm going to start on this topic. I hope this is enough motivation to keep you awake. That's been my goal. Hold on. Let me just fuss with this just for a second here. I don't need coffee. I'm nervous. Okay. All right. All right. Okay, so RG flows. Let's get to it. Okay. So Ken Wilson taught us to think about a quantum field theory, a general quantum field theory, as a flow from some UV theory to some IR theory. Okay. And the paradigmatic example of this is, of course, the example that Ken Wilson himself contributed so much to, which is QCD. Okay, and so in QCD, what's happening in the UV? Well, the beautiful discovery of asymptotic freedom tells us that in the UV, this theory becomes free quarks and gluons. Okay, now here I'm assuming that NF is less than 11 halves NC, right? Okay, so I'm assuming for sufficiently small flavors, this thing is asymptotically free. So it is a free theory. Okay, and a free theory, as we'll see later, is an example of a conformal field theory. It's a simple example of a conformal field theory. So what happens in the infrared? Okay, the first part of this picture is realized. We have a UV CFT. It happens to be free, and then what happens in the infrared? That's what the study of QCD is all about. Okay, so what happens in infrared? It depends on many things. It depends on the quark mass, the number of flavors, and the number of colors. Right? I don't put the QCD coupling because the QCD coupling just defines a scale, right? And I'm just going to work in units of that scale. Right? So these are the parameters of QCD. The quark masses, the number of flavors, the number of colors. So what happens? Let's go through some examples. Okay, the one that's closest to our world, it's basically our world, is NF is small. Okay, and you'll hear about what small means, but small means, for example, 2 is small. Okay, and the quark masses are non-zero. All the quark masses are non-zero. Okay, and all the quark masses are small, just for simplicity, are small compared to lambda QCD. If they're heavy, we can integrate them out. We don't change anything. Okay, so in this case, what we have is we get pions, right? And their mass is of order lambda QCD times quark masses. Okay, but for our purposes, all I care about is that they are non-zero. Okay, so these are non-zero, and so the theory if I go to energies below the pion mass, this theory has nothing in it, has no degrees of freedom. Okay? So this is a very particular, this is an empty CFT. It's a very especially trivial example of a conformal field theory. Doesn't have any degrees of freedom. It's sort of a degenerate case. Okay? We get a slightly more interesting case if we take NF to be small, right? But now let's take all the quark masses to be exactly 0. Okay? Then we have massless pions. We have massless Nambu-Goldstone bosons. Okay? And so these guys never decouple. Okay? So is this an interesting theory? Well, if we know what the low energy dynamics of the pions is, well below the QCD scale, and it is a nonlinear sigma model, and there are interactions among the pions, but they all look something like d pi squared, 1 over f pi squared. They are all irrelevant interactions. Okay? So at energies well below, this is for energies well below the lambda QCD scale, they only have irrelevant interactions which just go to 0 as a power law. So this theory actually in the IR, it asymptotes to just a theory of free scalars. Okay? You can call them free pseudoscalars if that makes you feel good. Okay? But it's a rather trivial theory as far as the infrared asymptotics goes. Okay? Now, yes, sorry. Well, they're confined. So the thing is that they're confined into glue balls and all kinds of hadrons that are all at the scale lambda QCD, which in our world is a GeV. So there are no actual physical massless particles, right? So the gluons behave like massive particles, but only when you're calculating processes at very, very high energies, right? So they're not actually massless. If we actually go to low energies, all we have are the pions, and if the pions are massive, we don't even have that. Yeah, then you do. I'm not, this is a theory talk, so I get to ignore QED. Okay? So the QED coupling is an interesting case because the QED coupling, as long as there's charged stuff, E goes to 0 in the infrared. So this is an aside on QED. Okay? So now the thing is though this running of the electromagnetic coupling, which is wanting to go to 0 in the infrared, is stopped, okay, if once you hit the mass scale of whatever particle is running in the loop, right? And so if you have massive particles, eventually, if all your charged particles are massive, eventually you get to integrate them out. And then you just have a free photon. So then you have a free theory, okay, which is now just a theory of free photons. You could have massless pions. So it turns out you might ask, well, what happens if I have massless pions that are charged? The answer is they can't be massless. They can't be exactly massless because they will at least get an electromagnetic correction to their mass. Okay? So you can go through these cases. There are many, many cases that we know of. Basically, so far what I'm telling you is if you have massless particles, you have a theory of free massless particles in the infrared from everything I've told you so far. Yeah? See, this is what's wrong with this generation today. Is all they want to do is fine-tune and make the lives of theorists miserable. Yes, you could. You could. Okay. In that case, you would have a different kind of a phase, because what you would be having is, but again, you notice that the electromagnetic coupling is going to 0. This is what's actually called a Coulomb phase. You can get natural versions of what you're talking about in supersymmetric theories. Okay. But I know you don't care about natural theories. Okay? Okay? So we can go through lots of cases like this where we get various kinds of massless particles, but from a theory point of view, these are massless free particles are not very interesting. We get something much more interesting if we look at NF is nearly 11 halves, okay, times the number of colors. Okay? That's where QCD loses asymptotic freedom, according to Wikipedia. Okay, but now I'm going to be not right at where it loses asymptotic freedom. I'm going to be at a little bit below. Okay, all right. Now I want to take epsilon small, And that only makes sense if NF and NC are large. Okay, so that epsilon being arbitrarily small makes sense if NF and NC are large. Then I can think of epsilon as more or less a continuous parameter, right? Okay, and so let me work in that limit. And in that limit, I should define a 't Hooft coupling. So instead of the QCD coupling, I should define to work with NC times the gauge coupling squared. Okay, this is the 't Hooft coupling. And the point about the 't Hooft coupling is that this thing here remains fixed as NC goes to infinity. Okay, and we're also going to take NF goes to infinity, right? Because we want to be in this ratio right here, right? This nearly fixed ratio. Okay, so now what does this theory do? I'm going to wander over here. This is always SUN gauge theory with NF quarks in the fundamental. Okay, it's what I would call QCD. Okay? Okay, so what does the beta function look like? I didn't look up the coefficients, but the point is that in the leading large n limit, n now scales out of the beta function equation, so there's no n dependence. Now the one loop beta function is still negative, but it's only negative by an amount epsilon. So we have a one loop beta function like this, right? But there's some coefficient of order epsilon in front of it. Okay? So now since this is abnormally small, because epsilon is just chosen to be abnormally small, I need to include the two loop contributions. Okay? And those things are some two loop factor. And there is no miracle that happens here. This thing is not of order epsilon. It's just of order 1. And it's also a positive number. It's just a fact. Okay? People have known the two loop beta function since time immemorial. Okay? And of course, I don't get to stop there. I also have 3 loop and higher contributions, okay, which become scheme dependent and whatever, doesn't matter. Okay? Now, let's look at this. Okay? So if I look at the beta function for this theory, right, beta as a function of g bar, for small g, for sufficiently small g, this term always dominates. Okay? So for sufficiently small d, the beta function starts off, of course, at 0 at g bar equals 0, and then it goes negative. Okay? But then for larger g, this term dominates. Okay? So it looks something like this. Okay? Sorry, it just looks like that. Okay? All right? Now we can ask, what happens if we start the theory in the UV here? So let's suppose we start in the UV here at the free fixed point. Okay? What happens is beta is negative. That means the g increases, right? And so g flows this way. But then it hits this place right here. Okay, this place here I'll call g bar star. It's some finite value of g, okay, g bar, where it now stops running because the beta function is 0. Okay? If I were to have started on this side here, I can see that the beta function is positive. G bar would decrease, so I would be pulled in this way like this. So if I started in the UV somewhere over here, I would also end up over here. Okay? This is an attractive infrared fixed point. Okay? All right? And the key feature of this is that beta of g bar star is 0. That's the defining feature of that. And you can see from this thing right here, by comparing these two things, that that means that g bar squared over 16 pi squared at the fixed point is of order epsilon. Okay? So it's small. So we're under control of perturbation theory. Okay? Perturbation theory is an expansion in this parameter, as you see here. And the higher loops are smaller, because this term is epsilon squared, this term is epsilon squared, this term is epsilon cubed. Okay, it scared me for a second. But it is epsilon cubed, right? Okay, so we have a fixed point, and at this fixed point, the theory just stays at g bar star forever, right? And it's interacting. It is not a free theory. So this is an interacting fixed point. Okay? Of course, it's perturbative, which is still a little bit boring for a theorist. Okay? If you're into exciting theory. Okay.
So if you start from G star in the UV, just stay there forever?
Yeah. Yes. So you could study that theory on its own as a complete theory of the universe, or of some universe. Okay? Okay, and one of the things that's really important here is that the fact that the beta function vanishes the beta function is the avatar or the sign of violation of scale symmetry. But because the beta function vanishes, this theory is invariant under scale transformation. So there's a scale symmetry, which is just x mu goes to lambda x mu. Just rescaling all the space and time coordinates, that is now a symmetry. So sitting here at this theory, if I sit here, I have an interacting theory that has an additional space-time symmetry, namely scale symmetry. That is starting to be interesting.
So we assume that all the fermions I think maybe the fermions are massless.
Yes, they're exactly massless here. I didn't say that, so thank you for asking. These are all completely massless, otherwise I would integrate them out at some scale. So these are, that's good. Here the m quark is 0, exactly 0. Okay? And I should mention that this is a famous paper from the 80s by Banks and Zacks. Okay, and this is called a Banks-Zacks fixed point. Okay? So now I want to argue that, in fact, there are also non-perturbative versions of this phenomena. Okay? And the argument simply goes as follows. Okay? Suppose I increase, what happens if I increase, sorry, just a second. Yes, sorry. Thank you for interrupting me. Who's it? Well, so it's parametrically, it's an expansion in this epsilon right here. Okay? So perturbation theory is literally an expansion in epsilon. So as long as epsilon is small enough to use perturbation theory, I'm okay. So I don't know, you tell me. Do you think epsilon 0.1 is small enough? Probably. Maybe 0.3 is not. Yeah, there is a complicated formula that depends on ratios of NF over NC in front of that, but it is, yeah, it's nothing special. Let's talk about this later. This is a more detailed question, and I'd be happy to discuss it with you, but I don't want to spend time in front of everybody, okay? But I really would be very happy to discuss that. But this is true. I assert that this is what I've said here is correct, okay? All right, yes?
If we compare this example to the other examples, this is more interesting because this actually has something happening in the IR.
Very good. You think like I think. Exactly. That's exactly the point I'm trying to make. This is much more interesting from a theoretical point of view, okay? This is a lot more like RS. Okay, so for example, in this theory, what's the dimension of psi bar psi?
3.
Wrong, because not in this theory. Not in this theory. In this theory, the dimension of psi bar psi is 3. In the boring free theory, okay, it's 3. Okay, but here, what I really mean by the dimension of this is how does this guy respond to a scale transformation? Okay, and it responds in a non-trivial way, and the dimension of this thing is something like 3 plus some order epsilon correction. So again, if epsilon is small, it's a small perturbative correction. But you can see it's starting to get interesting. And now I'm going to try to make it more interesting by increasing epsilon, if you guys will stop interrupting me, the way I asked you to. All right? Okay? All right, so let's think about, this is already kind of interesting. Let's think about what happens if I increase epsilon. Okay, well, you can see what's going on here. Okay, if I increase epsilon, this is my loop counting parameter. Okay, so eventually what happens is I don't have perturbation theory anymore, and I don't know what happens. Okay, and I know that eventually if I increase epsilon enough, I'm going to get back to one of these boring confining cases, right? So there's some value of epsilon, which is the biggest value of epsilon for which this phenomenon occurs. Okay, so there's some epsilon max, and that's the largest value to get an interacting fixed point. That value exists. Okay? Now, that value is also, at that value, I cannot use perturbation theory. Why? Because if I could, this argument would tell me I have a fixed point to all orders in perturbation theory. So if I don't have a fixed point, by definition, perturbation theory is breaking down. Okay? So there exists some value, okay, of epsilon max, some minimum number of flavors where this theory is just, barely has this phenomenon. And that is a non-perturbative 4-dimensional fixed point.
So you can say it again, but you can tune it until it breaks down.
Yeah, because if I make epsilon big enough, eventually I get, remember, epsilon big means I'm reducing the number of flavors. Eventually I'll get to like 2 flavors where I know I have confinement. So somewhere there's a biggest value of epsilon for which I get this phenomenon. Whatever that value is, perturbation theory is breaking down there. That is a non-perturbative fixed point. Okay? And so actually, people are looking for this phenomenon on the lattice, and Tom DeGrand here is one of the people who is a pioneer in this kind of study. You can do it not just for QCD, but other gauge theories as well. Okay? And there's this argument for the existence of a non-perturbative fixed point is rather indirect. In supersymmetric theories, there are many examples of this phenomenon given by Seiberg duality. So I'm not going to review that, but there's very, very strong evidence that these strongly coupled fixed points are in fact ubiquitous in supersymmetric theories. Okay?
Is it necessarily true that you have the epsilon max? Maybe, you can get close to some epsilon max, but as soon as you hit it, then already you're in the confinement.
Look, if I have it for some epsilon and I don't have it for other epsilon, then there's a maximum value where I still have it.
No, but you can have it for many epsilons, and then if some have epsilons, then
that's epsilon max. The last value for which I have it. Ultimately, epsilon max is discrete. There's some value which is the largest one for which this happens.
I think the student is thinking about the number of colors is discrete, and there is a smallest number of flavors for which you are in the conformal window, and a smaller yet number of flavors you are confined to. And Markus is imagining the NC goes to infinity limit, and so there is a continuum, but there is a place where there is a transition.
Yeah, and if it's discrete, there's still a largest value for which this phenomenon occurs. It's a discrete value. Okay? And at that value, perturbation theory is breaking down. Okay? Now, Tom is also right that strictly everything I've said is only valid in the large n limit. Okay? But in fact, there's lots of evidence that this phenomenon occurs even for finite n, for example, for lattice studies. And also in Seiberg duality, we have many examples where this happens also at small nc and nf. Okay, a finite range of values, and we see the strongly coupled fixed points, and everything is the way I've described. Okay, this is all motivation. Just reminding you. Yes.
Do we know how the beta function curve behaves as we continuously increase this?
So no, we don't. We only know it in perturbation theory, and then there are various lattice studies that tell us things about what happens for larger epsilon and finite nf and nc and so on. So we don't know very much. Okay? That's what my whole lectures are about. Okay? My whole lectures are about that. Okay. Okay, and so good. Okay? So now all of these examples, it's gotten more exciting. Okay, it's gotten more exciting. I hope you agree. But still, everything is some UV fixed point going down to some IR fixed point, right? All of these examples, every one of these examples, and like I said, there's a ton more of examples like this. There are many examples in 3 dimensions and so on. Okay. Now, but there's another very, very important aspect of RG flows that I need to mention, which is the reason that we care about them so much. As phenomenologist, I'm still a phenomenologist sometimes. And this is the idea of universality. I guess I can put that part up, right? Oh, la la. There we go. In case you missed it the first time. Okay, I just have to mention the idea of universality. Okay, so another very, very important lesson that was taught to us by Ken Wilson and some of his collaborators was that a very important feature of RG flows is that a lot of times very different UV theories flow to the same IR theory. Okay? So for example, in QCD, we have a theory of free quarks, gluons, and quarks, and it flows in the infrared to one of these theories. Pick your favorite one, okay, depending on the value of the parameters. Okay? But now it's very important that we can also write down lattice QCD, as again taught to us by Wilson. Okay? And this is some completely different theory. It's some theory that lives on a lattice. Okay? But nonetheless, what happens is that this flow rapidly converges and becomes indistinguishable in the infrared from this other flow, which is great because this is the theory we're actually interested in studying. This is QCD at finite energy scales. Okay? And so as long as we make this lattice spacing small enough, these things converge. Okay? And this idea that very, very different UV theories can have the same low energy physics, so that if you're interested in the low energy physics, you can study whichever of these is convenient. This is the idea of universality. And universality has some very, very beautiful examples in condensed matter physics. Remember that classical statistical mechanics is just quantum field theory Wick rotated, so it's really the same subject. And in classical statistical mechanics, we have this very famous Ising model, right? And the 3D Ising model is just some 3D lattice thing, okay? And there are different phases of the lattice model. Most of the time, it either flows to one or another kind of a free theory in the infrared, either an ordered or a disordered free theory. But if you tune the parameters just right, it flows to some IR fixed point, which you can study on its own. Okay? Now, the Ising model was originally invented as a theory of magnetism. It turns out it sucks as a theory of magnetism. Okay? It is not a good theory of magnetism. But it turns out that this IR fixed point right here, okay, is the same IR fixed point that you would find by taking phi-4 theory in 3 dimensions and carefully tuning a flow. So that's the first thing. Okay? These RG lines are never supposed to cross, so there's more dimensions than there are on the blackboard. Okay? So don't ask me about that crossing point. Okay? Things will get ugly. Okay? All right? So it's the same theory. So it's actually the low energy effective theory of a fine-tuned phi-4 theory in 3 dimensions. And it turns out it also describes the triple point of water. So the Ising model describes the triple point of water. And you can measure this very, very precisely because these funny dimensions of these operators, which are funny in one of these fixed points, they're not just some integers or half integers. These funny values can be experimentally measured by how you approach the fixed point. They're called critical exponents. And they can be measured, and they precisely agree to something like 6 digits from the Ising model computed either this way or this way. Okay? And in fact, just a sneak preview, one of the most precise theoretical determination of these critical exponents actually comes from this approach right here, not the lattice approach. People spent 20 or 30 years improving the RG methods. In the last few years, the conformal bootstrap, the techniques which I'm going to describe to you, have gotten more accurate using this approach. Okay? Yeah, so if you want to talk about this last bit I'm talking about in the conformal field theory, there's some excellent TASI lectures by David Simmons Duffin from I think last year or one of the last couple of years, which are truly excellent. Last year, okay? I'll be stealing from him wholesale when I get to that topic, okay? Okay, but now that we have opened the floodgates to more interesting flows, okay, we can ask the question, are even these fixed points too boring? Perhaps these fixed points are just too boring, okay? Let's not worry about the UV, because look, we've got this universality. Many different theories can have the same IR physics. We care about the IR physics, but we can have this, and now I'm going to reclassify this as being boring. Okay? What else could happen? Well, for example, I could have a limit cycle. Why not? Okay? I could even have some kind of a chaotic flow. Some fractal dimension flow. Okay? Could this happen? Could this happen? Okay? And Ken Wilson himself asked these questions when he was first thinking about RG flows. Okay? And so now what I'm going to tell you is that we actually know quite a bit about this. Okay? And into a large set of circumstances, which I'll explain precisely, we can rule out things like this. And in fact, the only thing that we have is this. Okay? That's what I'm going to tell you about. Okay? Questions? Okay, so how much time do I have left? Till noon. Okay. You guys don't want to eat lunch, do you? I didn't think so. Okay, intellectual food. All right. So now I'm going to switch from being grandiose and vague to being precise and perhaps painful. Okay? So we need to understand, we need to have the tools to understand these results. We need to be able to deal with this new space-time symmetry, which includes scale transformation, but as we'll see, it includes more. So I'm going to give a review of space-time symmetry. Okay? I'm going to pretend that you have not covered this topic in your your quantum field theory class. You did, but I'm pretty sure you didn't do it the way I'm going to do it. Okay? So try to put on a Zen mind if you can, and try to learn what I'm going to try to explain to you. Now, in particle physics or in quantum field theory, if you have some global symmetry, it is always, and I mean always, a good idea to gauge it. It's always a good idea. Okay? Whether or not the symmetry is actually gauged in nature, when you gauge it and you look at the response of the theory to these gauge transformations, you always learn something. Always. Okay? And in the case of space-time symmetry, we have global space-time symmetries like rotations, Lorentz transformations, translations, and we'll talk about these scale transformations. These are global transformations, but it's useful to gauge them. So we'll gauge them. How do we do that? How do we gauge space-time symmetries? We promote the metric to an arbitrary background metric. Okay? And this is just some arbitrary metric. It may or may not satisfy some nice equations of motion. And ordinary derivatives are replaced by covariant derivatives. Okay? And now we're going to be pretty general. We're going to be extremely general about what theory we're talking about. We're going to assume that whatever theory we're talking about can be the correlation functions of it can be computed by some path integral. Okay, so we have some fields, okay, which can be any collection of fields. I'm kind of drawing scalars. Phi kind of looks like a scalar to the naked eye, but it doesn't matter. It can be anything. And then I insert my operators, and then I just divide by the path integral. Okay? And the point is that the idea here is that I can do the path integral in an arbitrary background metric g mu nu. Okay? All right? And so I'll say that these correlation functions are computed with some background metric. Okay? And just to be clear, when I'm using this kind of notation, this sort of average notation, at least for this lecture, I'm in Minkowski space, and these are time ordered. Okay? So I'm not going to write all that time ordering out for you because I am lazy, but you should understand that it's there. Okay? Now, when we so the g mu nu is our gauge fields. What is our gauge current? Right? The gauge current is defined by differentiating with respect to the functionally differentiating with respect to the gauge field. And so in the same way, if I functionally differentiate with respect to the metric, I get a 2-index object, which is defined conventionally like this. Here's the square root of the determinant of the metric. Okay? I'm using some set of conventions that I'm only going to talk about if you pester me about it. Okay? There's an I there. Oh, actually, I think there might be, I don't remember. Anyway, it's probably wrong. Doesn't matter. Okay. The ideas are what's important. Okay? All right, and now the gauge symmetry, what is the gauge? So this is the current, right? Right? And what does this actually mean? What does this formula mean? It means that if I want to look at the correlation function of t mu of x with some number of other operators, okay, that is just going to be equal to the differentiating with respect to g mu nu of x with this stuff, 2 square root minus g, some I, if you want, of the correlator without the t mu nu in it. That's what this formula means, okay? And I'm always in practice going to be interested in flat space. So at the end of the day, I'm going to set g mu nu equal to eta mu nu after I'm done with all my differentiation. And so this, with nothing written here, this is in flat space. So there's a ghostly eta mu nu here, okay? Which you can't read. Okay, so that's what the current is. What are the gauge transformations? Those are diffeomorphisms. Right? They're diffeomorphisms. And how do diffeomorphisms act on the gauge fields, the g mu nus? They act as minus gamma mu xi nu plus z nu gamma mu. So this is a convention where the infinitesimal shift of the x's is some arbitrary xi, vector xi, which depends on x. And for example, a scalar field transforms as minus del rho phi, okay, and so on. You know what they are for higher spin fields, I hope. Okay. All right, that's pretty boring. Now, I want to make the connection now between these gauge fields and the actual global symmetries that are the actual symmetries that we have. And that connection is made through the Ward identity. Okay? And the Ward identity says that if I take d by dx mu of one of these correlators that has a t mu nu in it, and then it has an arbitrary number of other operators. This is the flat space correlator. Okay? If t mu nu is conserved, the right-hand side would be 0. It's almost, but not quite 0. Okay? What it actually is minus I, a delta function, x minus x1, times d nu O1 x1, O2 x2, etc. And then there's a term like this for every other operator. In other words, there's a term where the x, which is this guy, is there's a delta function with this x1, and then there's a derivative here. Okay? All right, this is the Ward identity. This is derived, this follows from the diff invariance of the path invariant. Okay? So this path integral that I wrote over here, once I put in the arbitrary gauge field, it is now gauge invariant. It is now diff invariant. And that diff invariance implies this relationship right here. Just like if I have a gauge theory, gauge invariance implies conservation of the gauge current. Okay? Okay? So now the way, when I see an equation like this, we'll see bunches of equations like this. The way I interpret this equation is that d by dx mu of this guy is just 0 as an operator statement. Okay? Okay? And what does that mean? It means that this thing is 0 inside arbitrary correlation functions as long as I stay away from these nasty coincident points. Okay? So as long as this x is inserted at a place where there's no other operator, it's just 0. Okay? That's what I mean by something is 0 as an operator statement, and you'll hear me say that a bunch of times. Okay? Okay. All right. Now, get some water. You guys aren't asking enough questions. So far, we have an enormous group of gauge transformations, which is labeled by 4 arbitrary functions, which is just an arbitrary distortion of the manifold. Okay? So I'm going to make the connection now to Poincare. Where is Poincare? Poincare is sitting inside of that. And I'm going to explain that just now. Okay? See, I'm one step ahead of you. Okay, so where does Poincare symmetry come from? Where is Poincare in all of this? Okay? Well, Poincare is the subgroup of this that leaves the metric invariant, the flat space metric invariant. Okay? So Poincare is defined by saying that the flat space metric doesn't change under these diffeomorphisms, which gives us this equation here, right? Because I can just use ordinary derivatives since I'm dealing with flat space. Okay? And this is called the Killing equation. And it's just because there was a person named Killing, not because it's anything evil. Okay? As far as I know, you can't use this to hurt anybody. Okay? And so this is just an equation that you can solve for xi mu. Okay? You can just ask, what's the most general solution to this? It's not very hard to see that the most general solution to this is just a constant a mu. That certainly satisfies this equation, right? And then the other thing you can do is do something that is linear in x mu, the x's, where you have an antisymmetric matrix. Okay? And it's pretty easy to see that that's the most general solution. And this tells us what we already knew, because what is this? This is just translations, space-time translations, right? And this is exactly Lorentz transformations. So we have discovered, for the 80th millionth time, that the symmetry group of flat space-time is the Poincare group. Okay? All right. Now, whenever we have and you could generalize this to other metrics that might have less symmetry. For example, a Schwarzschild black hole would have rotation symmetry, but it would not have boost symmetries or other, symmetries, space translation symmetry. So you can generalize this very easily to curved space, and that's really where Killing got famous. Okay? All right, so now so just again, speaking very generally, whenever I have a diffeomorphism like this, which is an isometry, so this is the Killing equation that tells me that this thing tells me I have an isometry, keeps the metric invariant, right? So for any isometry, I can define a current. Okay, so given a xi, which is an isometry, I can define a current, which is just T mu nu contracted with xi nu. Okay, I can just define that. Okay. And why is that a useful current? Because the claim is that it is conserved. Okay? So d mu psi, let's just compute it. That is d mu. I have one term where the d mu hits the T mu nu, and I have another term where the d mu hits the xi nu. Right? Okay? The first term is 0 because the current, the T mu nu is conserved. Okay? Away from coincident points. Yes? 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 Okay? And the second term here, I can rewrite it because T mu nu is symmetric. I can rewrite this just as the symmetric part. This is 1/2 T mu nu d mu xi plus d nu xi mu. And guess what? That's 0. Right? So for any isometry, I can define a current like this, and that current is conserved away from coincident points. Okay? Yes? It's a connection term. So for example, d mu xi nu is equal to d mu xi nu plus Christoffel symbol xi rho. That's right, exactly. So in the flat space limit, covariant derivatives are just ordinary derivatives. Exactly. Okay? Okay, well, if I have a conserved current, what would possibly come next? Conserved charge, of course. Yes, conserved charge. It's always what comes next, right? I hope you're not asleep yet because there's good stuff coming, I promise. All right? So okay, so now we can define the conserved charge, and now we're going to spice it up a little bit, okay? We're going to spice it up a little bit by, instead of defining the conserved charge by integrating over a t equals 0 surface, I'm going to integrate over some arbitrary surface. So I'm in flat space-time, but I can make a nice curvy surface that's some generalization of a t goes to 0 time slice. And then what is the generalization of the charge? Well, I'm going to integrate over this sigma, okay? And I'm going to write the integral like this, d sigma mu, where at every point I have some infinitesimal area element, okay, or three-dimensional volume element in 4 dimensions, which is perpendicular here, okay, and then I have T mu nu xi nu, or I just have my J xi mu, okay? And so conservation, again, tells me, so what does conservation of J mu tell me? It tells me that this thing right here is independent of sigma, right? Right? I'm assuming, as always, there is no interesting physics in surface terms at infinity in flat 4-dimensional space-time. So I'm always assuming that those vanish. Okay? Actually, that's not true. There's instantons. But anyway, I'm assuming that they vanish. I'm ignoring them. Okay? Okay. Very good. Very good. I said independent of sigma. I was gonna taunt you guys, okay? And you beat me to the punch. Not quite true, right? Because this conservation is only true if we're away from coincident points, okay? So now what we can do, we can look at an interesting situation. Let's look at a situation like this. Let's have some sigma final and some sigma initial, okay? So these are 2 different surfaces, okay? And now let's have a point x1 where an operator is inserted that's between these 2 guys, okay? And we can consider lots of general situations, but I'll consider the case where all the other points are up here, okay? So let's consider this. So now, between these 2 surfaces right here, okay, we have this point x1. Now, I cannot make this argument, right? I can deform sigma 1, but only as long as I don't cross this guy, right? Sigma initial. I can deform sigma initial, but I can't cross this guy. I can deform sigma final, but I can't cross this guy. What happens? Okay, well, you can easily figure out what happens. Okay, let's figure it out. So let's look at the integral from sigma initial to sigma final. We're doing the volume integral over this region here. Okay, that's what this means. And then I'm going to write d by dx mu of the g mu xi of x, O1 of x1, and then all my other operator insertions, which are later, right? Time is going this way in all my diagrams. So these are all later, okay? And so what is this? Well, this is pretty easy integral. It's an integral of a total derivative. So this is just the integral over sigma final. It's just the integral over sigma final, right? D sigma mu, j mu xi minus integral sigma initial, d xi mu. Same thing, same integrand, right? Just okay? Yes? Right? Okay. And then these guys there's all the other operators, right? Right? Okay. I don't care what by those. This is an integral of a derivative. You can have as many delta functions as you want. This is still true. I'll get to the delta functions though. Okay. Be patient, young man. Okay. All right. I'm still working, there's always a left-hand side and there's a right-hand side. The delta functions are on the right-hand side and I'm on the left-hand side. Okay, we're on the left-hand side here. Okay, so we have this, and let me actually, sorry I wrote this out so crappily, okay, but now it actually becomes important that remember that this is a time-ordered product, right? So the time ordering fixes the order of these 2 operators, right? Time ordering is later to the left, so who's to the left here? Who's later? Initial, x1 is later, right? So actually, this guy is actually to the left over here, right? Now how about in this term right here? It's in the correct order. So the time ordering is fixing the relative order of J and O, right? And so I claim the left-hand side is equal to exactly the commutator of q xi with O1 of x1, right? And all the other guys are nicely in there, just given by their time ordering. So that's the left-hand side. It is a commutator, right? Okay. Now, on the right-hand side, right, I have I can just plug in what I know that thing is. It's a sum of delta functions, right? And so the only delta function that matters is x equal to x1, right? Because I'm this thing. And so this thing is then equal to what? It's equal to I times the variation of the operator O1 with all the other operators in their place, right? Because this is just xi rho del rho O1, possibly with a minus sign. Yes? Okay? So in other words, this is another one of those operator statements that are true except for coincident points, because I assumed there was no other points in there. If there were more points in there, you get more terms, but you know what to do. But what I have now as an operator statement is that q xi O of x for any operator is just equal to I times the variation of that operator under that symmetry. Okay? And this is true as an operator statement, away from coincident points, etc. Okay? So this is something that you know and love, which you may not have seen in this much generality. Okay? This is the statement that conserved charges are not just conserved, they're not just good idea because they're conserved, but they also generate, I'm sorry, there's no vev here, sorry. This is just an operator statement, excuse me. Okay? They also generate the transformations of the fields. Okay? And this is just, so what I've shown you here is that this is a consequence of the Ward identity in a very, very general sense. Okay?
So that
setting.
Transformation property of the operator O1 is true even for any scaling dimension operator, or it's only true for?
I haven't said anything about the scaling dimension, so yes. The one thing I have assumed is that it's a scalar. There's no Lorentz indices on it. But it's true for any scalar operator of any dimension. That's correct. Okay? All right? Which you know is true, right? You know that's true. You can also show this using, canonical methods. Maybe that's how you showed it in your quantum field theory class. Okay, so now let me just summarize, and then hopefully things will get more exciting. This is standard stuff, but I want to have it under our belts so we can use it. So what do we actually have? We have the Poincare group. We have these two kinds of transformations, right, parameterized by a mu and omega mu nu. And for each of them, there's an associated charge. And of course, here, the charge for a mu, the charge is just the momentum operator, which gives me a minus d mu, whose commutator with this gives me just a shift. And then I have the Lorentz generators, which acting on a scalar field just do I x mu d nu minus x nu d mu acting on O of x. These are just the infinitesimal form of the translation and Lorentz transformations of fields. And from this, we can work out the commutators of the p's and the m's themselves. We can just apply repeated transformations on the fields, and we can work out the commutators. And we find that the p's commute with each other. That's obvious. They're just ordinary derivative operators. The m's and the p's do not commute. There's some minus I eta mu rho, p nu minus eta nu rho, p mu. Okay? And then there is the beast, the I eta mu rho, m nu sigma, plus or minus additional terms that just enforce the anti-symmetry separately in these two indices. This is a standard formula you can look up. Okay? So what I've done for you is I've started from the idea of a space-time isometry, an invariance of the metric, and we've gone all the way to figuring out how fields transform under it, and that there's some algebra of these transformations, which is the Poincare algebra. Okay? Any questions on this? Okay. All right. So that's pretty standard stuff. Okay? At least it should be. So now let's ask, okay, why did I go through all this? I went through all this because what I really want to talk about is scale symmetry. Okay, that's what I really want to talk about. Okay? So let's see if we can apply this to talk about scale symmetry. So what do I mean by scale symmetry? I mean the symmetry, the space-time symmetry that one of these fixed points has. So I mean this. I just rescale all the space and time coordinates by the same amount. So lambda is a constant, just like the a mu's and the omega mu nu's. These are just some space-time independent constants, okay? And immediately you see that there's a problem, which is that eta mu nu is not invariant, right? It's not invariant under this. In fact, it just goes to minus 2 lambda eta mu nu. It's not 0. Duh, right? We're rescaling lengths. The metric scales under that. It doesn't stay the same, okay? So clearly, everything that I've said before doesn't apply, okay? But we're going to apply it anyway, all right? Even though it doesn't apply, we're going to apply it. Namely, you can't stop me from defining the associated current, can you? You didn't stop me. You're going to stop me. Yes?
The fact that it's not an isometry doesn't mean that it can't be a symmetry of the path.
That's
So
true.
If you define the field transforming to cancel it, then
That's true. But here, I'm just saying what I did before. I didn't have to mention anything about how the field's transformed. It was just an isometry, and I got a conserved current, okay? This is the part that may seem a little bit perverse, but just bear with me, okay? Just bear with me. You may be saying, what on earth is he doing? But just look, watch. Okay, now let me just calculate the divergence of this, and it's probably sitting up here somewhere. There it is, right up there. Okay? This part of the calculation right here, okay? This part of the calculation right here, up until this point right here, didn't depend on this thing being an isometry. It just depended on the energy momentum center being conserved. Now, what is this right here? It's not 0, but what is it? It's minus 2 lambda eta mu nu. Yes? So what this thing is it's minus lambda of the trace of the energy momentum tensor. Okay? So what I find is that, okay, this gadget does give me a conserved quantity. It gives me a conserved quantity if I make this extremely strong statement that the trace of the energy momentum tensor is 0. And what do I mean by an operator being 0? I mean it's 0 away from coincident points, right? Read my lips, right? Okay? Okay? So now this is just like making stuff up, right? I'm just making stuff up here, right? Is this even plausible? Right? Is it even plausible that some theory would have this operator, which has every right to be a good operator, to be in fact 0? Okay? Yeah, exactly. You guys are just too smart. It's no fun lecturing to you guys. You're taking away all my element of surprise. You know? Let's check it for free field theories. Okay? See, I'm so predictable. All right, let's see. Okay, if this has any chance of being valid, we should check it for free field theories. Okay, and the first example we'll do, the simplest example, we'll do stay in 4 dimensions, and we're coupling it to a metric. Okay, so we can define the energy momentum tensor, and it's just d mu phi. Okay, possibly with a minus sign depending on my conventions. Okay, and anyway, the energy momentum tensor is the following famous formula, which you've seen many times. Okay, that is it. We breathlessly compute the trace, and it's non-zero. Okay, the trace is non-zero. Fail. But wait. Okay? The thing is that the T mu nu trace is 0, okay? But the claim is that T mu nu is not the unique 2-index conserved tensor in this theory. Why? Because I can define another object, which is O mu nu, which is d mu d nu minus box eta mu nu, all acting on phi squared. Okay? Now you notice that because I've had this transverse projector here, this thing is conserved. O mu nu is conserved. Okay? On the other hand, its trace is not 0. What's its trace? Well, I just get I get a 1 here, and I get a -4 here, so I get a -3 box phi squared. Okay? Now that trace is non-zero, but it doesn't look like this trace, right? But I haven't yet used the equations of motion. Remember, this thing is not even conserved unless I use the equations of motion, right? Okay? So the equations of motion are another thing that holds up to contact terms. Okay? So it's again, there's these contact terms, but the equations of motion are true away from contact terms. So using the equations of motion, I can write this as -6 d phi squared, because basically I write out this thing and the box phi, because box phi is 0. That's the equation of motion. Okay? So in fact, the trace is proportional to the trace here, and I can define a new guy, t tilde mu nu, okay, which is t mu nu minus 1/6 O mu nu. Okay? And that guy is traceless, and he is conserved, so I can use t tilde instead of t, and I can do this whole construction over here. I can define a scale current. Okay? All right. Alternatively, I could also define the theory by adding a non-minimal coupling to gravity. I could add some ds, d4x squared minus g, and then I can write an r of g phi squared. So this is the Ricci scalar. Okay? And then I can put the appropriate coefficient here, which I believe is -12. And if I put that coefficient in here, then this term, it vanishes in flat space, so it doesn't change the flat space correlation functions, but it affects the definition of the energy momentum tensor from differentiating with respect to g mu nu, and it exactly gives me t tilde. So I can also think of t tilde as arising from a non-minimal coupling to gravity. That has to be carefully chosen. Okay? So actually, scalars pass. Okay? All right? I'm mindful of the fact that I just have a few minutes left, and I won't make you late for lunch. So let's do another example. This is actually easier, which is a 4D gauge field. Okay, 4D free gauge field. We're just doing free theories. We're starting small, right? And what is the action? d4x square root minus g, 1/4, g mu nu, g rho sigma, f nu rho, f nu sigma. So, sorry, nu sigma. So you can, again, just by differentiating with respect to g, you can find the energy momentum tensor, and its eta mu nu is equal to, there's a term that's proportional to, f nu, rho, rho, and then there's a plus 1/4 eta mu nu f squared. Okay? And this nicely has vanishing trace. Okay? So now we're 2 for 3 because we've done free scalars, we've done free vectors, we have to do free fermions, and I'm not going to do free fermions for you. Why? Why am I not going to do it? Because if I had to do that, I would have to introduce Vierbeins, right? I can't use the metric formulation. I would have to introduce some of these guys. And you can do it. It's straightforward, and you find that the trace of the energy momentum tensor vanishes for fermions, free massless fermions as well. Always free and always massless, right? Okay? Now, I'm going to take just 2 minutes because I'm going to give you something that will, if you haven't seen it before, it will blow your mind, and I'll make you 1 minute late for lunch, but you'll get your mind blown if you haven't seen it before. Now I can ask the question. Oh, this is my favorite calculation right up here. Here we go. Here's my favorite calculation. I can now ask the question, what if oops, this thing got blah, blah, blah. It's got erased, but you've seen it a million times. Okay, what if I now require that this current be conserved? I say, I want it to be conserved, and the energy momentum tensor has 0 trace. Okay? All right, I'm very optimistic. I'm buoyed in optimism by these free field theory examples, and I think maybe this is an interesting class of theories. So if T mu nu is 0, what happens? Right? I haven't used anything. Now, what is the most general value of this such that this vanishes? It just has to be proportional to the metric. But the constant of proportionality could depend on x. Right? So I could have minus 2 sigma of x, any function right here, eta mu nu. It would work just as good. Right? Okay? So what I find is that, in fact, I have potentially a larger group of symmetries when the trace of the energy momentum tensor vanishes. I need to satisfy this equation. Del nu xi mu is equal to 2 sigma eta mu nu. And now this is an equation for both xi and sigma. They can both be arbitrary functions of x. Okay? And this is called the conformal killing equation. Okay? And I'm just going to tell you the solution, and then if your mind isn't blown, you'll just have to eat lunch and be a sad person without your mind blown. But the mind-blowing fact is that this equation has the following solutions. Okay, xi mu of x is equal to, actually I'm going to need my notes for the last term. Okay, of course, it includes what we had before, right? It includes the Poincare transformations. It also includes the scale transformations. We knew that, okay? And it includes exactly one more thing, which is the following thing. Okay? Now, how do you solve this? How do you do this? You can do this for yourself. I recommend it. Actually, it's a very good exercise. If you want exercises, one exercise is to derive this. I'll tell you the idea. You just expand in powers of x. Okay? And you'll just see that there's no, this is 0th order, 1st order, 2nd order, and you can easily see there are no more solutions at higher orders. Okay? So this is it. These guys we knew about, and these guys are WTF, right? What are these guys? And these guys are, I guess I can't say that. So these are called special conformal transformations. Okay? And so this is the extra unexpected space-time symmetry, which appears to emerge at the ends of RG flows, and that's what we're going to be studying next time. So I'm going to stop there. Okay? Thank you. Oh, sorry. Let me just write down one more thing. Yeah. Sorry. So this thing here is lambda plus b dot x, 2b dot x. So there's also a corresponding solution for sigma I forgot to write down. Okay, but anyway, we will discuss this next time. Okay, don't clap again.
So we will go through like A theory?
Yeah, we will. We will.